Hello, good morning. Again, continuation of our easy lecture series, lectures on modeling and realistic modeling and simulation of earthquakes, soils, structures, and their interaction. Joining me today again are, as usual, Dr. Han Yang and Mr. Heshan Wang.
Hi.
And today, this lecture will be about calibration of a steel model for 1D fiber modeling of reinforced concrete beams and reinforced concrete plates, walls, or bending plates, walls, in plane walls, and shells. So, Dr. Yang, Han, please share your screen so that we can get going.
Okay. Share screen. This one. Share full screen.
Good.
All right.
Great.
Can you see this? Yes. Okay.
Yep, perfect.
All right. Okay. Thank you, Professor Boris, and hello again for another again from Davis this morning. In this video, we're going to talk about the calibration of a uniaxial steel material model for a reinforced concrete beam column. Well, actually, it can also be used for shear wall, plate, or shells. So it's a really very versatile material model, and it's used a lot. So here we're going to talk about the command and also how to calibrate this material model. So first, just briefly review what does this material model do. So this material model, again, was developed by Meneghetto and Pinto in 1993 and later extended by Professor Filippo in 1983. This is the same material model, steel O2 material used in open seas. So if you already have calibrated that, you can directly use the same set of material parameters. It's going to give you the same results. And it's capable of capturing the nonlinear hysteretic behavior and isotropic strain hardening effect of steel. So here is the real easy domain-specific language, or a DSL command that you're going to use when you define this material model in your finite element model. So we say add material number, and then the type is uniaxial steel O2. So here are the list of material variables. So the first two are material parameters that can be directly determined from physical experiment, the yield strength and the elastic modulus. So usually when you have a structural steel, those numbers should already be given by the manufacturers. Or if you're interested, or if you want to do your test by yourself, then you can get a more direct number from your physical test. So other than those two physical parameters, you have a number of parameters, additional parameters that can be used to better shape your basically your stress strain behavior. So those material parameters that controls the shape of the loading, unloading, and also reloading path, they usually needs to be calibrated, but according to our experience, the default values usually works well because especially for steel rebars in most practical uses, you are only given those two physical parameters. So for all those additional parameters, some researchers or engineers would be a little bit confused as how to use them. But according to our experience, you can in most cases you can use the default values, and those recommended values are given here. So those are the recommended values. In most cases, you can directly use them. But I should mention that the material behavior is kind of sensitive. So if you don't have additional test data or more basis, so we recommend you to use the recommended values without changing them. Yes, please.
No, so this is really for standard reinforcing steel. So depending on what kind of reinforcing steel you have, these are good default values. These are good values for using that, but it's always a good idea to have more data and not to rely on default values. Rather make sure that these values that are recommended are working for your steel. Go ahead.
Yeah, that's true. Yeah, we highly recommend that you do have tests, but in case you don't, so you can use the recommended values. Yes. So here is a simple example of when you use this material model in your finite element model. So for reinforced concrete structures, you always have concrete and also have steel. So here, as you can see, this is the list of material models used for this specific case. So you have confined concrete, unconfined concrete, which we will talk about in another video. Here is the definition of the steel material. As you can see, it's the same format I've shown in the last page. So you have the yield strength, the elastic modulus. So those two are given by your physical test or from your manufacturer. So you put those values here, and then these are the additional material parameters. As you can see, we are using the recommended value for this case. So this is the response we get by using this steel material here. As you can see, we are calibrating our model behavior against a test done by Professor Hazelton and his colleagues in 2008. So as you can see, using this set of material parameters, we can get a pretty good match for the experiments. So, but again, when you have different cases, you probably have different responses. So it's recommended that you do the calibration by yourself and just try it out. Again, have a more feeling of how those parameters will influence your behavior.
Yes.
So yeah, so here are the references for this presentation, and I'd like to acknowledge my collaborators and fundings and collaboration from the funding agencies. And again, for more information, please go to the website of Real Easy. So it's realeasy.info. There's more examples, explanations, and menus and videos and all those informations you're going to need to run your simulations. And with that, thank you.
Thank you very much. So if you'll stop sharing your screen, I'll just say thank you, and we'll continue with this in our next lecture. But at the moment, I will just, let me see here, I'll stop recording.